Think of a globular cluster, and you picture an ancient, tightly packed sphere of stars burning brightly in the void, a dense, immortal cosmic metropolis. Look toward the summer sky, within the constellation Ophiuchus. Right as the map centers on the serpent-bearer, you'll find a target challenging that exact expectation. This is Messier 12. It sits roughly 15,000 light-years away and is hurtling toward Earth at 16 kilometers per second. But notice the structure. Instead of a blazing, impenetrable core, the center is loose. The stars are granular and scattered, lacking the intense spherical symmetry usually seen in these formations. Messier 12 is an active cosmic crime scene, a dying object violently stripped of its own stars. To understand what happened here, astronomers used the Very Large Telescope in Chile to conduct a high-precision photometric study, measuring the brightness and colors of more than 16,000 incredibly faint stars within M12. The data revealed a glaring anomaly. Based on standard models of star formation, there should be a massive population of small, low-mass stars. Instead, M12 is severely depleted of them. The numbers show that roughly 1 million stars have been physically ripped away from the cluster by external gravitational forces. This massive loss has drastically slashed the object's life expectancy. While typical, undisturbed globular clusters can survive for 20 billion years, Messier 12 will completely dissolve into the galactic halo in just 4.5 billion years. Grasping this structural degradation is the prerequisite to observing M12. Its violent history directly dictates the equipment and techniques needed to successfully photograph or view it. The cause of this destruction is M12's highly eccentric orbit. It dives straight through the dense, matter-rich plane of the Milky Way. Inside the cluster, a mechanical process called mass segregation is at work. The heavier stars sink toward the core, while lighter, low-mass stars migrate to the edges. Every time M12 crosses the galactic plane, it experiences intense tidal shock. The Milky Way's massive gravitational pull easily shears off those weakly bound low-mass stars. This continuous cycle of mass segregation and tidal stripping leaves the cluster heavily depleted. It has lost its dense outer halo, becoming a highly diffuse structure. But while the outer edges are stripped bare, the core experiences a different phenomenon. Stripping away the single, lighter stars has artificially concentrated a high population of massive binary star systems right in the center. These interacting binaries generate a dynamic heating mechanism. They actively push against each other, which halts core collapse and keeps the center of the cluster unusually open. That loose, unimpressive smudge in the eyepiece is a physical scar, the direct result of ongoing galactic tidal forces. So, how does this translate to practical observation? If you are setting up with binoculars or a small telescope under 8 inches, M12 is going to present a challenge. Small optics simply fail to impress here. The brightest stars in the cluster are only 12th magnitude. Without serious light-gathering power, the cluster remains a granular, unresolved smudge without a blazing center. If you want a satisfying view with a small scope, its close neighbor, Messier 10, offers a much brighter and more compact core that performs beautifully under lower aperture. However, if you upgrade to a large aperture telescope, something in the 10 to 16-inch range, the equation changes entirely. The diffuse nature of M12 becomes an asset. Because the core lacks that dense, blinding concentration, a large scope can resolve individual stars completely through the center, revealing a delicate, sprawling network across the field of view. M12 is an uncompromising, aperture-dependent target. It severely underwhelms beginners, but it highly rewards those who invest the money and effort into massive light-gathering power. For astrophotographers setting up their gear, Messier 12 looks like an easy, inviting target, but it's actually a trap. The initial data acquisition is incredibly fast. You only need about 1 hour of total exposure time, relying on short 30-second broadband shots to keep the dense stars from bloating. The trap springs when you look at your raw data. Relying on broadband imaging from suburban skies introduces severe light pollution and lunar gradients, completely obscuring the faint, tidally stripped halo of the cluster. Standard calibration won't save it. you have to use a complex software workflow known as synthetic flat field correction. You start by running a star extraction algorithm. This completely removes the stellar signal, isolating the flawed background sky and the diffuse glow of the core. Next, you apply multi-scale median transforms and clone stamps. This eliminates any residual nebulosity, building a pure mathematical model of your background gradient. Finally, you use pixel math. By dividing the original image by your new synthetic flat, you yield a perfectly flat, high-contrast field where the outlying stars pop clearly. The trade-off here is clear. Capturing M12 will save you hours of time in the field, but you will pay for it with an expert-level, math-heavy burden in post-processing to reveal the cluster's true structure. So who should invest time hunting down Messier 12? Let's look at the final verdict. If you are a beginner with a small scope, skip it. Pan 3 degrees southeast and spend your evening observing the denser Messier 10. With a 10-inch scope or larger, target M12. It perfectly tests your instrument's ability to resolve stars through a diffuse core. Astrophotographers, proceed only if you are prepared to execute advanced background extraction techniques in your software. Messier 12's uncompromising demands on your equipment and your skills aren't just quirks of the night sky. They are the direct consequence of its violent orbital history with the Milky Way. Observing Messier 12 allows you to witness the slow, gravitational death of a galactic fossil.